Good day, Dr. Aksha and Dr. Haslinda. Thank you for having us here today. We are from Group 3 and will be presenting Untitled 2, which is the design of a floating liquefied natural gas plant. The presentation is divided into 7 main parts. My name is Jasmine and I represent the first speaker to highlight mainly on the introduction and literature review content. LNG is achieved through pre-treatment and liquefaction of raw natural gas, where water vapor and the non-hydrocarbons are removed and sold separately as LPG, whereas the lighter fractions are liquefied to produce the bulk of LNG. Hence, FLNG plants are designed to facilitate these processes while retaining similar onshore process technologies. The advantage of an FLNG compared to onshore plant is that the processes are done on the unit itself, where compression units are not required, as well as having easy decommissioning capabilities. Moving on to the problem statement. Offshore gas fields in Malaysia contain huge amounts of H2S and CO2. The challenge here is to build a suitable process system to eliminate and treat the feed gas containing these contaminants. Next, sustainability of the plant is a factor as well, and processes are to be optimized based on achieving the highest recovery of hydrocarbons alongside enhancing energy consumption and profit. These are the main objectives of the project that highlights the optimum process route and technology, while emphasizing cost considerations and safety and environmental concerns. Next, in this project as well, unit parameters serves as inputs for the simulation of the plant using engineering software such as Aspen HYSYS and Visio. Heat integration analysis was also preceded using HIN software. Next, the literature review will cover on the market study and the plant location. Substantial increase of LNG usage in the power generation, mining and industrial sector is shown in the bar chart above, as over the past few years it continues to play a crucial role as a feedstock. A minimal increment is noticed in the transportation sector, as LNG fuel is slowly being adapted due to its low carbon dioxide APAP properties. And the average price of methane around the world is at $2.98 per gallon, and as of 2019, ethane is priced at $4 per MMBTU and propane $6 per MMBTU. Now, the average difference in these prices across the countries are due to various taxes, subsidies, as well as developing country status in terms of importing and exporting. Now, generally, the low fuel switching cost of LNG and a decline in the prices are boosting the industry growth from all three aspects. In terms of the global market demand, as stated by McKinsey, the world natural gas consumption growth has risen from 3.5 TSCM in 2014 to almost 5.2 TSCM as the year 2040 approaches. Sources from Shell has forecasted that the LNG demand is expected to grow 3.6% per annum till 2035, with market rebalancing expected to happen at the end of 2028. However, at present, worldwide LNG supply is around 340 MTPA and is estimated to reach around 680 MTPA as the year 2035 approaches. To date, Europe has absorbed majority of the 2019 supply growth, as low prices has enabled the switch of coal to gas source of power sectors. Now, strong growth is seen from Southeast Asia and will offset the demand declines of the mature gas markets of Europe and Northeast Asia. As of the Asian market demand, since Asia alone has been consuming 50% of the world's coal, thus having an urgent measure for carbon dioxide regulation has positioned most Asian countries an interesting spot for LNG imports. Now, the market is also facing competition from the US and Australian market, which is heavily dependent on supplies from the Middle East sector. Sources by IEEE in 2017 showed that Asia alone has been replacing conventional oil-fired power plants to natural gas-fired power plants, which contributes to the increase of LNG demand from 40 to 70 mm tons in the coming year 2030. Now, as seen in the graph, whereas for the past 5 years, LNG supply is significantly higher than the demand, which will result and create a favorable market for the LNG buyers. Malaysia is the second highest for the export of gas, and LNG alone is 4.9% of their energy mix, which deals out to a total of 15.8 ringgit billion, placing them fourth on the overall LNG world exporting list, as stated by WoodMac in 2019. Now, the decision in selecting the strategic location will affect the feasibility, efficiency, and long-term performance of the plant. Some of the primary factors to be considered here are the raw materials, market availability, and water supply, whereas the secondary factors are the transport facilities and labor supply. A comparison was done amongst Rotan, Kanowe, and Kebambangan. Rotan field has 7 gas fields, and this has been an area of interest as discovered by Murphy Oil Corporation. The field is situated 140 kilometers offshore Kota Kinabalu with a natural gas capacity of 349 billion cubic feet. And Kennewick, on the other hand, has a cluster of 10 gas fields and is situated 200 kilometers offshore Bintulu with a natural gas capacity of 550 billion cubic feet. And lastly, the Kebabangan cluster are relatively new and has 6 gas fields. The cluster comprises of these fields and is positioned 130 kilometers offshore Kota Belud with an expected natural gas capacity of 2 trillion cubic feet. The weightage criteria ranges from 1 to 5 in order of importance. Based on the decision criteria of the comparison table, it is concluded that the Kebabangan field of Sabah is found to be the most suitable location. Now, the raw materials availability and the water supply were the prominent criteria at 1.5 million tons per annum and having more than 2,500 meter cube of water respectively as compared to the other two fields. The field was also the nearest to the offshore facility as compared to the rest of the fields. And based on the current global demand and production gap, the plant capacity is estimated to be 1.5 million tons per year with a running plant operation of 330 days. Hence, the selected site of Kebabangan field, which comprises of 6 wells, a natural gas capacity of 2 trillion cubic feet, is able to accommodate the required plant capacity and sustain the LNG demand for over 20 years of the plant operation.
Assalamualaikum and good day. My name is Muhammad Afiq and I will proceed with conceptual design of our LNG offshore plant. So in this part, I will be explaining about the process screening, process flow diagram, mass balance, and economic evaluation. Alright, so for the first part, which is pre-treatment, it can be divided into 4 parts, which is slug catcher, MRU, which is mercury removal unit, AGRU, acid gas removal unit, and DHU, which is dehydration unit. And for the first one, slug catcher, what we desire is we want the slug catcher to save space and fast installation, and it must be suitable for feed gas which has high gas to liquid ratio and for feed with steady flow. And the technology that we have chosen for slug catcher is vessel type compared to finger type, and this is the operating temperature and pressure, which is around 16.7 to 48 degrees Celsius and 15 bar gauge respectively. And the next one is MRU, more compact bed and efficient mercury removal is what we desired, and absorbent, not affected by liquid water and liquid hydrocarbon. And the technology that we have chosen is non-regenerative compared to regenerative, since the mercury is not that much in our feed inlet, and the operating temperature and pressure is 32 to 68 degrees Celsius and 25.7 to 79.7 bar gauge respectively. The next important process unit is AGRU. Basically, we want AGRU to provide less than 1% hydrocarbon loss, and it can remove both carbon dioxide and hydrogen sulfide H2O and H2S, CO2 and H2S, and we use DEA where it does not suffer degradation and also decomposition. And the technology that we have chosen specifically for AGRU is absorption and stripping compared to membrane separation. And the operating temperature is 30 to 60 degrees Celsius, and the operating pressure is 5 to 120 bar. And next is DHU. Basically, we want excellent dew point depression, and we want the unit to be able to handle sour gases, do not absorb heavy hydrocarbons, and high porous and very high surface area. And the technology that we have chosen is molecular sieve, where it can be regenerated compared to absorption and also condensation. And the operating temperature is around negative 50 to negative 448 degrees Celsius, and the operating pressure is approximately around 5,000 kilopascal. Alright, next we'll proceed with natural gas liquids recovery, NGL. So it can be divided into 2 parts, which is demethanizer and also liquefaction. And for demethanizer, we want better concentration of light components, conserving overall energy and also utility saving, aids liquefaction, process to obtain higher purity of the product, and the technology we choose for demethanizer is CDWC, which is conventional divided walled column compared to top divided walled column, and the operating temperature and pressure is negative 63 degrees Celsius and 1200 kilopascal respectively. And the next one is liquefaction, where we want to liquefy methane from vapor to liquid phase, and it must utilize non-flammable hydrocarbons in refrigerant cycle, where it will reduce the safety hazards, high simplicity, and high flexibility to ease the startup and shutdown operation. And the technology we have chosen is single nitrogen expander, compared to mixed refrigerant and cascade. And the operating temperature and pressure is 30 degrees Celsius and 5000 kilopascal respectively. Alright, next is process flow diagram, PFD. So for our plant, for our LNG plant, the rate of production that we are planning is around 1,409,081 pounds per year, and the plant will operate around 330 days, considering 35 days to be spent as for turnaround or maintenance, and the assumptions for LNG that will be produced is 90% CH4, 9% C2H6 ethane, and 1% C3H8 propane. And from this PFD, it can be seen a few major units, which is slug catcher, MRU, AGRU, DHU, demethanizer, and liquefaction. And from the feed inlet, we will go through. Firstly, we will go through slug catcher, where condensate and also water will be majorly removed from the natural gas, and natural gas will proceed to the next unit, which is MRU, mercury, where mercury will be removed, and then it will proceed to the next major unit, which is AGRU, acid gas removal, where CO2 and also H2S will be removed, will be mainly removed. However, while we are removing H2S and CO2 by using solvents, which is DEA, some in the stream tank, there are some natural gas the remaining natural gas will also go with the H2S and also CO2. That's when we will use stripping column to separate the remaining natural gas to be used as utilities, and it will proceed. The impurities will proceed to the distillation column, where we will regenerate the amide and separate the CO2 and H2S for the uses. And the amine, the DEA, will go back to the absorption column to be used for the absorption. After it is absorbed, the sweet gas it will result into sweet gas, and the sweet gas will proceed to the dehydration in order to remove the water inside the natural gas. So in here we proceed with two adsorption column using molecular sieve, where one absorption column will be used as standby, and one will be in running. And if the running is saturated with water, then it will regenerate again by using the regen gas, and another adsorption column will be used for this adsorption of water. Then after the gas has been dehydrated, we proceed to the demethanizer, where it will separate methane from ethane and propane. So from here, ethane and propane will be in vapor phase, and ethane and propane will be in liquid phase, and methane will be in the vapor phase. So as we want to liquefy the methane, it will proceed to the next unit, which is liquefaction, where the temperature of methane will be decreased extremely in order to make the methane liquefied. And the last stream indicates the liquefied natural gas, which mainly consists of methane. Next is mass balance. So basically from the mass balance, I will just go briefly. So we can see the outlet of this, after it will go through MRU, the outlet of this natural gas is 0. That means total separations, complete removal of mercury. So compared to M is indicates as manual and S indicates as simulation. So basically the manual and simulation is the same, where complete removal of mercury is obtained. Next is AGRU, where we want to separate CO2 and also H2S. So from manual and simulation mass balance, the H2S presents complete removal after it go through AGRU, and also a small amount of carbon dioxide is still in the natural gas, less than 1% overall in the overall amount of the natural gas. So it is suitable for the suits the consumer's requirement. Alright, for the next one is dehydration. As you can see here, as the inlet is 150,000 in the manual and 163 in the simulation, and both of these after dehydration both displayed 0, which is complete removal of water. So the natural gas is totally dehydrated without containing any water. And the next one is demethanizer, where we want to separate methane from ethane and propane. And from here we can see outlet 1, which is only methane, which totally methane in the manual, and also mainly methane, which a very small number of ethane, and outlet 2, which is mainly ethane and also propane. Next is liquefaction. So basically we just want to convert methane from vapor phase to liquid phase, and the amount is still it doesn't have any losses during the liquefaction. Alright, so the next part is economic evaluation. So for the utilities, we are considering chilled water, steam, cooling water, and also electricity, and the subtotal is around 63 million ringgit per year. And the raw materials that we are considering is DEA solvent and liquefied refrigerant, which is nitrogen, which with the amount of 231 million ringgit per year. And the fixed capital cost is 210 million ringgit, and the general and manufacturing is 122 million and 394 million ringgit respectively. And the estimated product cost that we have produced, that we are planning to produce, is LNG is around 7 billion ringgit per year, and LPG is around 117 million ringgit. And from these values we can calculate EP1, EP2, and EP3, where EP1 with the formula of product plus byproduct minus with the raw material, and we have obtained for EP1 is 7 billion 520 million ringgit per year, and for EP2 with the formula of EP1 minus utility, and we have obtained 7 billion 456 ringgit Malaysia per year. And the EP3 with the formula of EP2 minus annual manufacturing cost with the very sustainable amount for this plant, which is 7 billion and 61 million ringgit Malaysia per year. So from this amount, it ensures the sustainability and relevancy of this plant to be operate at the industrial level. So I'll proceed to the I'll pass to the next presenter to present about the heat integration. Thank you.
Hi, my name is Amrila binti Ismail, and now I will continue with the heat integration part. So there are four subtopics under this section, which include stream data, heat cascade, composite and grain composite curve, and also heat exchanger network. So here it is the stream data that we obtain from our HYSYS. So as we can see here that there are 7 streams, where 5 of them is the hot stream, meanwhile 2 of them is the cold stream. So basically the type of stream can be determined based on the placement of heater or cooler. So generally cooler is used at the hot stream to reduce the temperature of that specific stream, and same goes to heater where it is used at the cold stream to increase the temperature of that specific stream. So for the specific heat capacity here, we obtain from the average value of the Cp in and out of each of the stream. So we use this formula to calculate the specific heat capacity. Okay, for the heat flow is calculated based on this formula where we multiply the Cp value with the temperature difference of the stream. So for this project, we use delta T min is equal to 10. This is because the range of temperature from 10 to 20 is widely used in various type of industry, including the refinery. So moving on to problem table method. So as we can see here that we find or determine the interval temperature of supply and targeted temperature by using this formula. So as we can see here that the hot stream basically will reduce the interval temperature for the hot stream will be reduced by 5 degrees Celsius, meanwhile the cold stream will be increased by 5 degrees Celsius. As the delta T min is 10 and then we divide by 2. So basically this interval temperature will be used later on for the heat cascade process. Okay, so next is heat cascade. So as we can see here that the temperature that listed here is from the interval temperature from problem table method earlier. So by conducting heat cascade, we may able to determine our QC min and also QH min. But for our case, we don't have QH min, which is the minimum hot utility. This is because our process is only considered for below pitch. And from here, we also be able to determine the pinch temperature, which is 116.6 Kelvin, where the heat flow is recorded at 0 kilowatt. Okay, so moving on to composite curve and grand composite curve. So here, as we can see here, for composite curve, there are 2 main lines, which is the red line and blue line. So red line is resemble for the hot stream, while blue line is for cold stream. So the combination of these two lines will be used to generate grand composite curve as this line. So for the grand composite curve, we may be able to determine our QC min, as we can see here. This is our QC min, and this is the pinch temperature where it is recorded at 0 kilowatt. Okay, so this is the PFD before heat integration. So as we can see here that our process, we have 7 main utility where 2 of them is heater. This is the heater, and the remaining 5 is the cooler. So this is before heat integration. So after this we will see what are going to happen to our PFD after we conduct the heat integration process. Okay, moving on to heat exchanger network. So for our project, our case, we don't have above pinch. This is because all of the stream data is below the pinch temperature. So after conducting the heat integration process, we have new additional heat exchanger, as we have been removed the heater from these two cold stream, while we have 5 the remaining or the existing cooler. However, for these two cooler, its duty have been reduced because some of the heat have been transferred or exchanged through these two heat exchanger. So here is the PFD after heat integration. As we can see here that we still have 7 utility, but this one is we have two new heat exchanger which replace the heater. So this the duty of this cooler, this 1, 2, 3, is the same. However, the duty of this cooler here and here is reduced because we have been transferred the heat from this hot stream to be exchanged with this cool stream. So that's why our cooler now will be reduced in terms of its duty. So as we can see, as a summary, as we can see here that for hot stream, before heat integration, our core utility is around 2,765 megawatt. After heat integration, we have reduced up to 2,300. So, which means that we save the energy is around 462 megawatt. For the core stream, before heat integration, we have 462 megawatt. However, for the core stream, after heat integration, we have 0 megawatt. This is because we have removed the heater so that there is no longer hot utility on the cold stream. So the energy saved here is 462 megawatt, which is the same as the energy saved for the hot stream. So in total, we will have the energy saved is around 924 megawatt.
Hi, my name is Muhammad Zulzad. So I will proceed with the instrumentation and control strategy. For the control strategy, we have 4 types of control strategy. The first one is a feedback controller. The second one is a feed-forward controller. The third one is cascade controller, and the fourth one is ratio controller. This control strategy will mention more based on the major equipment and also the minor equipment. So the first major equipment, we have a slug catcher or a 3-phase separator. We have 3 types of control strategy. First one is flow controller, where we control the flow rate, inlet flow rate of the flow coming into the slug catcher. And then we have a pressure controller, where we control the pressure of the slug catcher. This pressure controller is in feed forward, where it's the controller is controlling the gas flow rate coming out of the slug catcher. We have also a condensate and water outlet. So for this, we have 2 types of feed forward flow controller, and it's connected to the ratio controller, where this ratio controller is controlling the composition of the outlet. Next we have an absorber. For absorber, we have 3 types of control strategy. First one is pressure. So for the pressure, we control the pressure of the absorber, where it is in feed forward, that the controller is controlling the gas coming out or the gas flow rate coming out of the absorber. Then we have a level controller. This level controller is to control the water level inside the absorber. So it's also in feed forward, and it's control the water flow rate coming out of the absorber. Next we have a flow controller, where it's control the flow rate of the liquid solvent that coming into the absorber. So we have a distillation column. For distillation column, it consists of 5 types of control strategy. First one is flow controller, where the inlet coming into the distillation column is controlled by the flow controller. So the flow rate is controlled by a feedback flow controller. And then we have a temperature controller. For 2 and 3, temperature is for the condenser and also for the reboiler. So these 2 temperature controller is in feedback control. Then we have a pressure controller. Pressure controller is used to control the pressure of the distillation column, where this pressure controller is in feed forward, and then the
the controller will control the flow rate of the gas coming out from the distillation column. And also we have a level controller that control the level water level inside the distillation column. This controller also in a feed forward control. So the level controller will control the water flow rate coming out from the distillation column. And then we have the absorber. So for the absorber, we have two types of flow control. Two types of control strategy. The first one is flow controller. This flow controller in feedback, where we control the flow rate of the inlet entering the absorber, and also we have a pressure controller in the feed forward, where it's control the flow rate of the outlet out from the absorber. For the mining equipment, we have a mixer. For mixer, we have two types of flow controller in the feed forward, where it's connected to the ratio controller. This ratio controller control the composition of the inlet. And then we have a heat exchanger. For heat exchanger, we have only one type of controller. So for it's in feedback, so the temperature controller will control the heat exchanger. So for the PNID after heat integration with the control strategy, so you can see here for mixer, the ratio controller. So this one is separator, heat exchanger, and also we have distillation column, absorber and also the strategy.
A very good day to my evaluators and thanks to my partner Izzat for passing it to me. Today I, Rashminder Singh from Group 3 would like to continue the presentation with the hazard analysis and plant layout section. Basically there were three nodes chosen for our hazard and they were the slug catcher, which is a three-phase separator, the mercury removal unit, which is an absorption column, and lastly the demethanizer, which is a distillation column. However, only the very important nodes will be discussed for this presentation, and they are the slug catcher and the mercury removal unit. So these two nodes are selected because they are very important as they are the front units of the process. Any failure in the slug catcher can cause the shutdown of the whole process, and any failure in mercury removal unit can cause the whole process to be contaminated with mercury. Therefore, let's begin with the slug catcher. One of the most important parameters in a slug catcher is the flow. It should also be noted that the flow and level are quite similar. The guide word used here would be more and less, and the deviation would be more and less flow. Therefore, the consequences of high flow may be due to the high feed, due to well surge, or due to the malfunction of the control valve before the separator, and the consequences of this will cause flooding in the separator and pipes also may rupture. Therefore, the best safeguard would be to have an emergency shutdown system or a relief system which would mitigate the extra feed elsewhere. Moving on, if there is a less or no flow, this may be due to blockage in the feed pipeline, due to solid hydrates or thick slug. This would cause the separator to be inefficient and production rate to be low. The best safeguard to this problem would be to have a proper control system in the feed line, so any major reduction in the feed can be noticed. The best action would be to manage this less flow or more flow problem would be by having high quality and accurate level alarms in the separator, and lastly the other two parameters for the slug catcher are the pressure and also the level, which can be seen more detailed in the report. Now moving on, there is the mercury removal unit. The important parameters for the mercury removal unit are flow, pressure, and also temperature. However, the one that affects the efficiency of the absorption column or mercury unit is the pressure and also the temperature. Usually at higher temperatures and pressure, the absorption process will be more efficient. Therefore, the pressure and temperature had to be included in the hazard. So for further details regarding the hazard, the report can be used as reference. Next, moving on with the plant layout. Several considerations should be made when designing the plant layout for a floating liquefied natural gas FLNG production facility. The main parameters considered during the design are usually the safety issues, self-sufficiency, technology with cost-efficient viability, and also marine motion resistance, and lastly compactness of design. Other than that, the FLNG has to be designed in a way that it divides into two areas. And those two areas are the process areas and non-process areas. These areas will be shown later based on the layout. Firstly, the zone areas in a FLNG will be explained. The FLNG plant consists of processes involving flammable hydrocarbons. Therefore, the FLNG has to be categorized into three zones. And those three zones are zone 0, where the indicator is red, and then there's the second zone, which is known as zone 1, where the indicator is yellow, and lastly there's also zone 2, where the indicator is green. And this zone is considered to be the safest, as the explosive or flammable gas atmosphere occurs only for a short time or not at all. Zone 0 with the indicator red is the most dangerous. Now let's move on to the layout of the FLNG. So as I mentioned earlier, there are two areas in the FLNG. First is the process areas and also the non-process areas. And this, as you can see here, is the side view of the FLNG plant. Lastly, this is the top view of the FLNG plant. Now with that, I end the plant layout. Now I would like to pass to my partner to conclude the presentation. Thank you.
Okay, for the conclusion part, I would like to conclude that our plant location chosen is at Kembambangan field in Sabah. This is because this location is chosen as it able to accommodate the capacity of 1.5 million ton per year with the plant operation of 330 days. Our FLNG plant seems to be feasible because we obtained the EP value of 7 billion ringgit. Our plant is designed to accommodate 170,000 kg per year of global market demand with the purity of methane around 99.3%. So the selection of the technologies that have been done in our project is through the comparisons with the other alternative and finalize the best option for our plant. So the total of energy saved for our FLNG plant is around 924 megawatt after conducting the heat integration process. So for the recommendation, there are two recommendations. The first one would be the improvement study in order to minimize the cost and to improve the maintenance of our plant. The second one would be the optimization study to correlate the energy saving in terms of efficiency for both production and economical.